Laws of refraction. The phenomena of refraction of light takes place according to the following three laws. The incident ray, the normal at the point of incidence, and the refracted ray all lie in the same plane. When light goes from one medium to another, the frequency of light does not change. However, the velocity and wavelength of light change. The ratio of the sine of angle of incidence to the sine of angle of refraction is constant for the two media. Thus, from adjoining figure we have sin I upon sin R is equal to constant is equal to A, mu B, equation 1. This constant A, mu B is called relative refractive index of medium B, in which refracted ray travels with respect to medium A, in which incident ray travels. Equation 1 is known as Snell's law and holds good for all angles of incidence. The refractive index depends upon the nature of the two media and the wavelength of light. The shorter the wavelength of light, the greater is the refractive index. Thus, the refractive index of a medium is greater of violet light, shorter wavelength than that of red light, larger wavelength. Laws of refraction. Absolute refractive index. The absolute refractive index of a medium is defined in the following two ways. If the incident ray is traveling in vacuum and to a good approximation in air and is then refracted in a medium, then ratio sin I by sin R is called absolute refractive index of the medium, that is, absolute refractive index mu is equal to sin I by sin R. The absolute refractive index of a medium is also defined as mu is equal to velocity of light in vacuum upon velocity of light in medium. For example, the absolute refractive index of ordinary glass is 1.5. Mu is equal to velocity of light in vacuum upon velocity of light in medium, or 1.5 is equal to 3 into 10 raised to the power 8 whole upon V. Therefore, velocity of light in glass V is equal to 3 into 10 raised to the power 8 whole upon 1.5 is equal to 2 into 10 raised to the power 8 meter per second. Laws of refraction. The greater the refractive index of a medium, the smaller is the velocity of light in it and vice versa. A medium that has higher refractive index is called optically denser medium, and the one that has smaller refractive index is said to be optically rarer medium. The refractive index of most common glasses used in optical instruments lies between 1.46 and 1.96. There are very few substances having indices greater than 1.96, diamond being one with an index of 2.47. Refraction through a parallel slab. When a ray of light passes through a parallel-sided transparent slab, the emergent ray is parallel to the incident ray, although there is a lateral displacement. Consider a parallel-sided slab KLMN having parallel faces KL and NM as showing in figure. A ray of light AO in air, medium A is incident on the glass surface KL, medium B at point O. The ray bends towards the normal and follows the path OB. At point B, again refraction takes place and the ray bends away from the normal, emerging out of glass, following path BC. It will be shown that the emergent ray BC is parallel to the incident ray AO. At point O, sin I1 upon sin R1 is equal to refractive index of medium B with respect to medium A. Equation 1. At point B, sin I2 upon sin R2 is equal to refractive index of medium A with respect to medium B. Equation 2. Multiplying equation 1 and 2, we get A mu B into B mu A is equal to sin I1 upon sin R1 into sin I2 upon sin R2. But A mu B into B mu A is equal to 1. Therefore, sin I1 upon sin R1 into sin I2 upon sin R2 is equal to 1. Now, R1 is equal to I2 alternate angles. Therefore, sin I1 upon sin R2 is equal to 1, or sin I1 is equal to sin R2, or I1 is equal to R2. Thus, when a ray of light passes through a parallel-sided transparent slab, the emergent ray is parallel to the incident ray. However, it is laterally displaced. The sideways displacement D as shown. Expression for lateral displacement. We shall now find the expression for lateral displacement d from B. Draw BD perpendicular to AO produced. Let angle BOD is equal to delta is equal to deviation on refraction at surface KL. In triangle BOD, sin delta is equal to BD upon OB. Therefore, BD is equal to OB sin delta. Equation 3. In triangle OEB, cos R1 is equal to OE upon OB. Therefore, OB is equal to OE upon cos R1 is equal to T upon cos R1, where OE is equal to T is equal to thickness of glass slab. From equation 3, BD is equal to 1 upon cos R1, sin delta is equal to T sin I1 minus R1 whole upon cos R1, since delta is equal to I1 minus R1. Therefore, lateral displacement d is equal to BD is equal to V sin I1 minus R1 whole upon cos R1. It may be noted that lateral shift increases with first, increase in thickness of glass slab, second, increase in the value of angle of incidence, and third, increase in the refractive index of slab. Refraction through a compound slab. Consider a parallel-sided compound slab consisting of two media B and C and placed in a medium A as shown. A ray of light AO is incident on the interference of A and B at an angle I. The ray bends towards the normal and follows the path OB. Then it falls on the interface of B and C, water glass, and again bends towards the normal following the path BC. Finally, the ray emerges along a direction CD into the medium A. Since the various interfaces are parallel, the angle of emergence will be I. Let R1 and R2 be the angle of refraction in water and glass respectively. At the interface of A and B, we have A mu B is equal to sin I upon sin R1, equation 1. At the interface of B and C, we have B mu C is equal to sin R1 upon sin R2, equation 2. At the interface of C and A, we have C mu A is equal to sin R2 upon sin I, equation 3. Multiplying equation 1, 2 and 3, we get A mu B into B mu C into C mu A is equal to sin I upon sin R1 into sin R1 upon sin R2 into sin R2 upon sin I is equal to 1, or A mu B into B mu C into C mu A is equal to 1, or B mu C is equal to 1 upon A mu B into C mu A, or B mu C is equal to A mu C upon A mu B, since 1 upon C mu A is equal to A mu C. Thus, knowing the refractive indices of any two media, B and C, with respect to air, the refractive index of medium C with respect to medium B, or vice versa, can be determined. Real and apparent depth. An object placed in a denser medium, when viewed from a rarer medium, appears to be at a lesser depth than its real depth. It is on account of refraction of light. Consider a point object O at the bottom of a beaker container water as shown. Suppose xy is the surface that separates air and water. A ray OA from O perpendicular to the surface xy passes straight through into the air along AD. A ray OB very close to ray OA is refracted at point B into the air away from the normal in a direction BC. When viewed from above, the rays will appear to come from point I, which is the point of intersection of OD and BC produced backward. Thus, a virtual image of O is formed at I. Therefore, the depth of the object will appear to be AI. The depth AO is called the real depth of the object, and depth AI is called its apparent depth. According to Snell's law, W mu A is equal to sin I upon sin R is equal to sin BOA upon sin AIB is equal to AB upon OB whole upon AB upon IB, or W mu A is equal to IB upon OB. If point B is very close to point A, that is, when viewed from vertically above O, then IB is equal to IA and OB is equal to OA. Therefore, refractive index W mu A is equal to IA upon OA, or A mu W is equal to OA upon IA is equal to real depth upon apparent depth. For example, the refractive index of glass is 1.5. Therefore, a glass slab will appear to be only of 2/3 of its real thickness when viewed from vertically above. Apparent shift. If the real depth OA is equal to T, then apparent depth is equal to T upon A mu W. The apparent shift OI is equal to D of the object is given by apparent shift D is equal to T minus T upon A mu W. D is equal to T into 1 minus 1 upon A mu W. Apparent shift depends upon first, real depth of the object T, and second, refractive index of the refracting medium. Atmospheric refraction. Because light travels slightly faster in vacuum than it does through air, light from the sun or the stars is refracted if it enters the Earth's atmosphere obliquely. Since the atmosphere is denser near the Earth's surface, a ray of light coming from the sun or a star continuously bends towards the radius of Earth. Atmospheric refraction is responsible for a number of optical illusions. Atmospheric refraction, apparent position of sun. Because of atmospheric refraction, we do not see the sun or the stars in its true position except it is directly overhead. As a ray of light from the sun enters Earth's atmosphere at B, it continuously bends towards the radius of the Earth. The ray of light will reach the observer at O as if it had come in the direction AO instead of in its true direction BO. Consequently, we do not see the true position of the sun. It is due to atmospheric refraction that the sun is visible before actual sunrise and after actual sunset. The sun appears to rise 2 minutes before the actual rise, and it continues to be seen 2 minutes after it has actually set. Therefore, the day becomes longer by 4 minutes due to atmospheric refraction. Atmospheric refraction, twinkling of stars. When the rays of light from the stars enters Earth's atmosphere, they meet a medium of increasing density. As a result, the rays of light continuously bend towards the radius of Earth. Since the layers of air are not stationary due to convection currents, The image of the star keeps changing its position. These shifting position of the images of the star gives us an impression that the star is twinkling. However, the planets being nearer do not twinkle. It is because the amount of light from them is quite large, so the variation is not noticeable.